So I quickly wanted to give an overview of probability to help you with task 3 and what it means. Sometimes humans don't correctly calculate probability. They believe that, um, if something's very memorable, that is, if they see a news story about a plane crash, they'll overestimate the probability of plane accidents. When actually, considering all the flights in the world, it's a safe mode of transportation. Or they have they get confused about linking things together. And okay, if this happens, what's the odds of another conditional event happening? So I thought I'd talk about probability since it's asking you to figure out experimental probability for task 3. I wanted to include that in the lesson. So theoretical is determined but based on reasoning, logic. So we have a dice. So the theoretical probability of rolling a 6 is 1/6 because there's 6 sides. There's the number 6 is on one of them, so you can look at a 6-sided die and hopefully you understand the probability of rolling a 6 is 1/6. If we have a deck of cards, the theoretical probability of drawing any card and getting a spade is 1 in 4. Because there's 4 suits, one of the 4 suits is a spade. If it's all been shuffled, then each suit is equally likely. So then we have experimental probability based on the results of an experiment. So if we say drew 6 cards from the deck and we had 2 spades, well, based on the experiment, drawing the 6 cards, 2 out of 6 would be 1/3. So we would say, oh, the experimental probability is what 1/3, and so that's different from theoretical. Or if we were to roll a dice and we rolled the dice 4 times and got a 6 once, we would say the experimental probability of getting a 6 is 1/4. Now that may not totally match the theoretical logic-based probability, but the more times you do the experiment, the closer you will get. So for example, if we're thinking about what's the odds of a TTC delay, if the bus is late on Monday and Thursday, then the experimental probability of being late is 40%, 2/5. And then the more experiments that are conducted, the closer it gets to theoretical probability. So if we were rolling the dice 100 times, we should come up, it's probably going to come up with 6, 14, 15, 16, 17, 18 times, something close to the theoretical 1/6 probability. So you'd like to practice this, go to the Google random number generator, just enter Google random number generator, and pick your number, your favorite number. And so the theoretical probability of getting that is 1 in 10, right? There's 10 possible numbers. Yours is one of it, 1 in 10. So generate the number 10 times. What's the experimental probability? It may not have come up at all. It might have come up 3 times. As you keep repeating it, so if you did it 20 times, it should come up 2 times. As you keep doing it, you should keep coming closer and closer to the theoretical 1 in 10. So sometimes results of an experiment may not match theoretical probability, but make sure you do it enough times and have big enough data so there's no surprising results. So Bayesian probability is a conditional probability given the occurrence of another event. So it's like if you wake up late, will you be late for school? You're not going to be late every time. Sometimes you might run and still catch the bus, or the bus might be a minute late and you still get it. So, for example, here we have 2 different events. So, the chance of event A happening is zero point 0.7, because you can see the 0.4 plus the 0.3 is 0.7. So there's a 70% chance A will happen, and there's a 50% chance B will happen. But since A's already happened, what are the odds of B happening? Well, you can see um, of that 70% of A happening, there's 30% belongs to cases when both A and B happen. So 3/7 would be, what would that be? 482, so 43%. So if um, if A happens, it's actually 43% of a chance that B subsequently occurs. So here's an idea. 50% of rainy days start off cloudy, but 40% of all days start off cloudy. Typically, it rains on 10% of days, but we have to cancel our picnic if the chance of rain surpasses 1/4. So it's already cloudy. Should we cancel the picnic? What do you think? Well, we would want to use a little formula. So, um, the probability of um, rain given that there is a cloud. That's what we're trying to figure out, and we can use this formula here. So the probability of it raining on any given day is 10%. So replace that P event B with 10%. The probability of cloud when it's raining is 50%. So put zero point 0.5 there at the top, and then the probability of any cloud is 0.4. And if you run that through, you end up with the probability of rain today is 12.5%, because there's still some days where it clears up. Although half of cloudy days end up rainy, it doesn't rain that much overall, only 10%. And so this is probably going to be one of those days where the clouds clear. So that's a Bayesian or conditional probability. Sometimes I like the idea of how people think. So Daniel Kahneman and Amos Tversky. Uh, Kahneman won a Nobel Prize. Tversky had already passed away. Kahneman also wrote a book called Thinking Fast and Slow. Proposed that people are terrible at calculating realistic probabilities. Like if you asked someone, "Hey, what are the odds of this happening?" They would have no idea, because they have biases, they have preconceived notions. So one of them is the availability heuristic. If something can be vividly recalled, it seems more likely than more common but less interesting events. So, something that's on the front page of the papers, you're going to think that's more likely than all the stuff that's not worth, being in the news. So, car accidents are actually more common, but we see so many of them, they're not that interesting, we don't make a note of them. But then you see a big plane crash and it's in the headline news, so you think of it more, and it becomes more available to you, hence you give it a greater likelihood of happening. Another one, the representativeness heuristic. People use prototypes to determine if something belongs to a category. Rare characteristics are overestimated, and common characteristics are underestimated. So people create these gender and racial stereotypes. They overestimate the chance of catching, say, a rare illness, versus the compared to the chance of, just having heart disease or arthritis or something that's very, very common. they underestimate their chances of getting that because they remember the one person who got a terrible cancer, but they don't think of all the family members who started suffering from arthritis over the years because it's too common and it doesn't fit into their mind. And this is the stereotype. You say, don't judge a book by its cover. This is what the representative heuristic means. And lastly, anchoring or adjustment. When guessing a value, people are sensitive to numbers that they have encountered before and adjust from there. So a very simple example is if you're asked half the people what's 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1, they give much higher guesses than people asked the same question but in reverse order. Or if you just show someone a number, and like if I asked you to think of your phone number and then asked you, I don't know, what's the average mark in this class, those of you with phone numbers with high numbers would guess a bit higher than those who have lower digits in their phone numbers. So here would be an activity like that. How many students at the school study music? What's the population of Toronto? How many Tim Hortons locations are there in Canada? And these are some things, how would we guess them? So just try to think of a guess. I'm going to pause for a second. Well, what are the answers? The answers are in the speaker's notes. So 375 students from year to year, about 26.7% study music. About 6 million people live in the GTA, and there's about 4,300 Tim Hortons locations.